Okay, so here we go. So back to where we left off. So really we are now in the heart of we're in the heart of chapter 12, which is the differential rate law, and that's what we're going to work on today. Okay, so can you guys see those at home? Can you guys see this? The notes?
Yeah.
Okay, so this is where we left off. So we did this, and what we were doing, just to review, we were talking about the differential rate law, and we said this is how in chemistry they define the rate, and it's based off the reactants and their initial amounts, and you have to be given a data table, and the whole key is to determine the coefficient or to determine the exponents. I keep saying the coefficients because that's what we do in equilibrium, to determine the exponents, and we're going to do that more today. But here's the bottom part of this page. So the bottom part of this page, and again, so what we're going to do today is just continue on. We are now in the heart. There's two really main ideas in chapter 12, and we are now in the middle of one of those two. It's called the differential rate law. This again is not on the formula sheet, and I would recommend, like I said yesterday, I would recommend on your formula sheet, guys, where it says kinetics, I would go back and just write over here to the right, the differential rate law, rate is equal to K times A to the X and B to the Y, just like we talked about yesterday. And the way AP is making it sounds like you probably the AP test, unless something changes. And I was watching some news reports yesterday, and they're saying COVID cases are going down, COVID hospitalizations are going down, COVID deaths are going down. These are all really good news. So hopefully that trend will continue, which means that we will be more on a normal schedule. Who knows, maybe back at some point to a normal schedule. I'd have to wear a mask to do that. I would do it. But this is, so those of you that are home, the bottom, I just put up the bottom part of the page. So it says if the rate law is rate is equal to K times A to the first or B to the zero. And I'm going to go over today. It's actually the last thing I'm going to do today. I'm going to talk about what it means if it's zero order, first order, second order, third order. The orders are always going to be whole numbers. And again, it's going to be zero, usually one or two, but occasionally it could be three. So, but if think about it mathematically, anything raised to the zero power is what? Is one. And so if something is to the, and I'm going to go over all of this today, but the rate of the reaction is independent of B because it's to the zero order, which means anything to the zero order is one. So the rate of the reaction is independent of B. Changing B will make no difference to the rate of the reaction. Okay, so I want to do another one of these. Not that these are that hard, but they're new. There's something that is new here. So, and this data table is in our book, actually, so I should look it up. Let me see if I can find the page that is on in the book. So if you just want to say C page, or you can write it down. I think this is in our book, though. Yeah, no. It's on page 570. So if you wanted to say just see page 570, you can, or you can write it down. I'm just going to give you a minute to do that.
For the rate equation formula, would you need to only have two variables in there, or could you do it?
We're going to do it through. We're going to do it through. Yeah. So what I want to do here, that's Jordan, that's a really good question. But this one, remember what we talked about yesterday. So how they, chemists, rates, we've seen rates of reaction. We've seen some that have been very fast, both yesterday and today, and some that were slower. especially the colder water with the Alka-Seltzer. But how they determine the rate again is like miles per hour. But they base it off at the beginning of the reaction, the concentration of the reactants. And Jordan asked a good question. This reaction has 3 reactants. So that means it has 3 parts. So we're actually going to find the rate law, which simply means the equation. And since it has 3 parts, I'm going to do the first one. I'm going to kind of do the second one we'll do together. And then the third one, I'm going to have you guys do, okay? So, and again, not that these are hard, but these are new. And this is definitely the kind of thing that's on the AP test, that's going to be on our test, on our quiz. And actually, the lab we're going to do, the penny lab, is going to be with this rate law called the integrated rate law. It's going to be connected to that. But I just want to do the penny lab first. The sulfur lab, which we'll do next week, is more about this. So what we're going to try and do is we're going to find the rate is equal to K times bromate, BrO3 negative, to the X, bromide to the Y, and H plus to the Z. So the trick in these problems is to figure out the exponents, the X, the Y, and the Z. And like I talked about yesterday, is in doing these, if we can, and I'm actually going to show you some tomorrow, maybe Friday, where it gets a little bit more complicated. But right now, I just want to get the foundation down. So if I want to find the X, I want it when the bromate, the BrO3, changes in one of the experiments or 2 of the experiments. But the Br negative and the H plus are constant because they're not connected to the X. So I want to do this again when the Br negative and the H plus don't change, but the bromate does. And so the combination for finding X would be experiment 1 and 2. Okay, and for those of you at home, in 1 and 2, you can see bromate changes, but bromide and H plus don't. Okay, so I'm going to find the X. So in doing this, I'm just going to use this. So I'm going to use experiment right here. So, and I'm going to do, I always do this where I have the larger number on the top. I want to do it with the larger number on the top. To me, just those whole numbers make more sense. So I'm going to write in the rate. So for experiment 2, way over to the right, it's 1.6 times 10 to the negative 3. Okay, and now I'm just going to plug in the numbers. So the bromate is 0.20 to the X. The bromide is 0.10 to the Y. And the H plus is 0.10 to the Z. So I'm just plugging in the numbers for experiment 2 into the rate law. Okay, now I'm going to do the same thing for experiment 1. So I've got 8.0 times 10 to the negative 4 equals K times 0.10 to the X, 0.10 to the Y, 10 to the Z. Okay, so when I did this, and I don't need to do this as long in the other 2, but I do it where the exponent, its molecule, whatever I'm trying to find, that's what I want to change, but I want the other ones that exponent is not connected to, if I can, to be constants. So what I can do then is I can cancel out the K, I can cancel that out, and I can cancel that out, because it's all going to be the same. And so really, once you start doing this, on ones like this, you don't need to write it out as long as this. You could just do this over this. So you've got 1.6 times 10 to the negative 3rd over 8 times 10 to the negative 4 equals 0.20, 0.10 to the X. Okay, take a minute, solve for this. And these for us, and maybe in college, they will not come out to whole numbers, but I bet they will. So X comes out to be 1. So we would then say, going back up here, then the X is 1. So this is first order, and I'm going to talk about that here in a second. This is first order in terms of the bromate ion. And if I'm going too fast or there's something at home you can't see, let me know. Okay. Okay, now let's go on to bromide ion. So just take a minute again. If you haven't got this written down, I'll let you copy that down. Okay, so for bromide ion, let's kind of do this one together. So now, and again, the whole key here in doing this, when you have a concentration versus rate data, you're finding the differential rate law. It's all about figuring out the exponents. You have to be given data to do it. Okay, so we're going to do Y's. Let's kind of just do this together. So I want this where the bromide, the Br-1 changes, but the bromate and the H plus are constant. Okay, so what combination should I use of experiment 1, 2, 3, 4? 2 and 3, right? 2 and 3 is right because the bromate stays the same, the H plus stays the same, but the bromide and the rate change. So I don't have to write it out quite as long. Now, in looking at this, I agree with Liza and you guys, 2 and 3. Which should you put on top, 2 or 3? 3, because it's the bigger number. So I'm going to do experiment 3 over experiment 2. So I'm not going to write it out as long this time because I know the bromate and the H plus are going to cancel out. So I've got 3.2 times 10 to the negative third over 1.6 times 10 to the negative third is equal to, and again, I'm not going to write in K or BrO3 negative or H plus. I'm just going to go 0.20 over 0.10 to the 1. Okay, solve from there. Mark, you're right. You can almost do that without a calculator. And a lot of times on the AP test, I think on the AP test, I'm sure that on the multiple choice, they don't let you use a calculator. So they give you problems like this where you really don't need a calculator. And then the free response, they let you use a calculator. What's the value for Y? It's 1, right? So you have 2 is equal to 2, and Y, so Y is 1. So this is first order in terms of bromates. Okay, now you guys determine H plus, determine Z. Okay, so I'll let you guys figure out the best combination to use here. To do that. Okay, so in determining Y, what's the combination I want to use? 4 and 3. I thought it was 4 and 1.
Either way.
Well, I want to make sure that
Oh, wait.
you really could do, you could have done, Liza, you could have done 4 and 3. I'm going to talk about one like that tomorrow or the next day, but probably 4 and 1, right? Because in 4 and 1, the BrO3 negative and the Br negative are constant, but the H plus is changing. And I would put, and remember the exponents, when you're figuring out which number is larger, the first thing you want to do is look at the exponents. So 3.2 times 10 to the negative 3 is larger. So I'm going to do experiment 4 over experiment 1. So I've got 3.2 times 10 to the negative 3 over 8 times 10 to the negative 4. And again, I'm just going to include the part of the reaction we're looking at, which is the H plus. So I have 0.20 over 0.10 to the y. So these numbers come right here, right here, and I really don't need to include the BrO3 negative and the Br negative. What's the value for y?
Z.
Or z? Thank you, Tyler. Z. What is the value for z? It's 2, right? So here I get 4 is equal to 2 times the z, so z is equal to 2. So this is second order in terms of H plus. And again, we're going to do some more of this just because this is really, this and this other rate law are really the heart of this chapter. Okay, now questions there. Are we okay with that? At home, any questions? We all right? Okay, so now what I want to do, it doesn't say this, but let's determine the value for K. Let's determine the value for K. And one thing that I messed up with in my second period class, and I need to go back and do this, is the units on K are important too. But I can choose any experiment. I should get the same thing, 1, 2, 3, or 4. Cole, which one should I choose? You just tell me, 1, 2, 3, 4. 3. Cole says 3. I could have chosen 1, 2, or 4, but let's do what Cole says. So experiment 3, so I'm determining the value for K, and we're going to determine the numerical value and also the units. So, okay, so for K, it's 3.2, the rate, times 10 to the negative 3. And the unit here, if you look over there on the right where it says rate, it says moles per liter times seconds. Well, moles per liter is molarity. So that's molarity per second. This is a lowercase k. And again, that's going to become important in chapter 13. Probably not next week, but the following week. That'll be a capital K. Okay, bromate is 0.20. And the unit on this is molarity for the first. Bromate is 0.20 to the first. And H plus is 0.10 squared. Okay, so now we're doing algebra. So I just am solving for K. So I have 0.20. So I'm just showing you the algebra here. So I'm going to divide everything off of the right except for K. I am solving for K. So what I have here then is I have 0.20 molarity to the first, 0.20 molarity to the first, 0.10 molarity squared. Okay, solve for K. Let's do the numbers first, but then we're going to look at the units as well. And probably the trickier part is the units here. When I did this, I got 8.0.
Yeah.
So the value for K, the numerical value, and I need 2 sig figs. Everything in this problem has 2 sig figs. So Liza got that, so I feel like I'm okay. So I just took this, divided by that, and that squared. Okay, now the units. So here's molarities per second. So I'm just going to write this out. So I have molarity, and then molarity squared. So molarity times molarity. So what that does then is this cancels out. And what that leaves me is 1 over molarity cubed times seconds. And this is actually something, like I said, in my period 2 class, I forgot. I'm going to talk next about what the different orders of reactions mean. The one thing I forgot to talk to them about, and I need to do that tomorrow, are the units on K. The units on K change depending on the order of the reaction. Okay. Okay, so next slide. Okay, I want to get through this slide, and I'm going to actually add some more to this. Okay, so what do the orders of reactions mean? Okay, again, so the speed of reaction, what effect does the concentrations, or say something's first order, second order, third order, or 0 order, what does that mean? I'm actually going to write some stuff on the board here too, to kind of go over really the 4 cases we'll have: 0 order, first order, second order, third order. I don't know if they did this when they made, where in the new Star Wars? Wasn't that Kylo Ren? Wasn't he from the third order? The first order. He was from the first order. I don't, one thing, if you guys want to, and we get after spring break, I think I showed you guys some of my shirts that we've had in past years. Last year was a bummer because of the virus. We weren't able to do it. But I always let them design it. And as long as it's PG-ish, I'm okay. I actually was on a trip a couple weeks ago. My son competes in CrossFit. We're down in Austin, Texas, and I came across this one, and I'll show it to you guys. But sometimes in doing that, my students have kind of went, and we never had it as the final thing, but something to do with the first order. So, chemistry term. Okay, so in this reaction here, let me just be patient here for those that are taking notes. Okay, so in this reaction, and remember the key thing in doing this is to figure out those exponents. And we do that with experimental data, where we have concentration versus rate data. But the differential rate law, the rate, in this case, since A is raised to the first, it is first order. I'm going to talk about what that means here in a second. It's almost like you guys will kind of know just mathematically what that means. Since B's exponent is a 2, it's second order with respect to B. And since C is 0, it's 0 order with respect to C. Okay, so I'm going to add some stuff here. I'm just going to write some stuff on the board. So what order means? Okay, we're going to go over 0 order, first order, second order, third order, and that's going to be it for today. Okay, so if something is 0 order, like C is here, then a change in the concentration of a reactant has no effect on the rate. So what we would say here is the rate is equal to K times A to the 0. So if anything raised to the 0, it's 1. So as the concentration of A changes, it doesn't affect anything. One thing that I forgot to do, and I need to do this tomorrow with my period 2 class, are the units on K. And sometimes that is the clue as to the order of the reaction of the units on K. And the units on K here are molarity per second. Because if you think about this, if rate is molarity per second, and this is raised to the 1, it has no effect, so it's just molarity per second. Okay, first order. So if something is first order, that means something's raised to the 1. So here the rate is directly proportional to the reactant's concentration. So rate here, the way we would write this is equal to K times A to the first. And so this way, in terms of X, this is just X. So as A goes up, rate goes up by the same rate, the same ratio. And hopefully you guys can get to process the units here. But if you think about this, so if rate is molarity per second, and this is molarity, and if I'm solving for K, so if molarity cancels out, what I'm left with here is 1 over seconds. Sometimes that's written like this, seconds to the negative 1. So if it's first order, the units on the rate constant would be 1 over seconds. Okay, if something is second order, here, so the concentration of the reactant squares change in the concentration it squares the rate. So if something is second order, it's having a bigger effect on the rate. So rate here is equal to K times A squared. This would actually be 4x because of the squared thing. Okay, then the units. So again, if you think of rate as molarity per second, and then I've got K, and here I've got molarity squared. So if I cancel out again, if I'm solving for X, what I get here is 1 over seconds times molarity. And again, sometimes the clue that's given to the order of the reaction are the units. Okay, this could also be written like this, seconds to the negative 1, molarity to the negative 1. Those mean the same thing. Okay, and then the final thing, third order, and here a change in the concentration. Whoops, that's where we will pick up tomorrow. Okay, guys, good job. Remember your pennies and log in tomorrow. I will see you guys.
Thank you,
We'll
Mr.
see you guys again on Friday. You got it, Tyler. See you. See you guys. Hey, see you, Cole.
See you later.
See you guys.
I'm sure.
Hey, see you, Lexi. Have a good day.
Have a good one, Mr. Wood.
You too, Jack. See you Friday.